Welcome. Today we're going to do one of our buoy lecture series, Space Physics and Astronomy section. And the first up is going to be SM24A, the Van Allen lecture. And before we do that... They can't hear you. Oh, well, there's all these microphones everywhere. None of them work. Now, can you hear me? You read me 5 by 5? Okay. So what we're going to have to do is crank the mic setting up, if we still have our AV person here. Fran, if you do your speaking, please speak right into the microphone from very close. So, good thing. Thank you very much for the feedback. So we wanted to mention a couple of events that are happening today, if we could only advance the slides. Well, you know, life is like that, isn't it? Well, it is what it is, okay? So Fran will be introduced by Tom Cremegis in just a second. And I did want to remind you there are a couple of events this week that are relevant to SPA. I'll only take a minute. The reception is in the Marriott Metro Center, and it starts at about 6:15. You don't have to rush over there. It's not a race, but it is right after this. And it is in the Metro Center. And I do want to remind you that the Metro Center is not the Washington Marriott at Metro Center is not the Marquee, which is over here by this convention center. We are here at the convention center. It is about a 10-minute walk down to the Washington Marriott at Metro Center. And it is Salon A and B. So please attend. We appreciate that. And then directly after Fran's talk, we will have David McComas deliver the Parker Solar Heliophysics lecture. And it would be on the interstellar interaction observations and discoveries. So with that, Tom, would you like to introduce Fran, please? And we are going to try. Don't fall off. There we go. I'll leave that up. Please be careful.
Okay, thank you. Yes, there is no light here, or there is, maybe. I don't know if it works, or is that not the light? Is it light? Or is it the mic?
You would think that there should be.
Okay, well, it's a great pleasure and distinct honor for me to introduce to you Dr. Fran Bagenal, this year's Van Allen lecturer. Fran was born and grew up in England, in case you couldn't tell from her accent, and studied space physics at the University of Lancaster. In 1976, inspired by NASA's missions to Mars, and most importantly, the prospect of the Voyager Grand Tour mission, which what ended up being, to explore the magnetospheres of the giant planets, she decided to head for MIT to do her graduate work. Now MIT was the PI institution for the plasma instrument, the plasma science instrument, PLS for short, where it was being built under the leadership of Professor Herb Bridge. So she received her PhD in 1981 on the analysis from that instrument that basically delineated the existence of the properties of the now celebrated Eoplasma torus that we have seen so much work on for the past, I guess, 30-some years. It was during the Jupiter encounter operations on Voyager 1 that I first met Fran as a bright and somewhat quote spunky, I'll explain that, graduate student from MIT, along with another fellow from MIT you all know by the name of Ralph McNutt, but that's another story. I'm not going to get into that. At that time, there was a small issue between the plasma instrument and our own team's low-energy charged particle experiment, where a stepper motor that rotated every few seconds would induce a minor vibration in the grids of the plasma sensor, producing some minor noise, in my judgment. So Frank joined the argument enthusiastically and was persuasive in helping to limit the LECP stepper movements. It has been a characteristic of Frank's tenaciousness in arguing for the things that she believes in strongly. And those of us who have gotten into a spirited discussion with Frank know that firsthand. But we have since made up. Anyway, Fran went back to England after her PhD and worked at Imperial College for a few years. But the call of Voyager flybys with Uranus and Neptune proved irresistible. So she returned to become a professor at the University of Colorado at Boulder in 1989, where she has been ever since. Soon she was involved with the Galileo-Jupiter orbiter and then joined the team of the Cassini-Huygens Saturn orbiter while taking on the advocacy of a mission to Pluto with Alan Stern and Ralph McNutt that resulted in the New Horizons mission, as we all know. In the process, Fan also joined the Deep Space One mission to Comet Borrelly, and she's also a charter member of the Juno science team. I will not delve much into Fran's work as a leading modeler of the physics of plasmas and interpreter of observations in the magnetospheres of the outer planets, from Voyager to Galileo to Cassini to New Horizons and now Juno, of course. But I want to point out that Fran has performed invaluable service to the community by being a leader in the organization of the series of conferences known as Magnetospheres of the Outer Planets, MOP for short, that began in the 70s and continue to this day. In fact, the last one was again organized by Fran this year in Boulder, of course. But she's also an editor of volumes such as Jupiter, Planets, Satellites, and Magnetospheres, Cambridge University Press in 2004, and a key contributor to several other volumes on planetary magnetospheres. In addition, she was the initiator and chair for several years of OPAG, the acronym stands for Outer Planets Assessment Group, that pulled together ideas from the community and worked on advocating future missions to Europa, Enceladus, Titan, Uranus, and Neptune. So, ladies and gentlemen, this year's Van Allen Lecture is a colleague that combines incisive knowledge of the plasma physics of planetary magnetospheres, is a participant in all the major NASA missions to the outer solar system, an indefatigable teacher and mentor of the new generation of researchers in the field, and an organizer and leader of the community in the quest for future missions to the outer planets. Let's welcome Professor Frank Bagenal, who will speak to us about planetary magnetospheres 60 years after Explorer 1. Thank you.
Thank you, Tom. And if the people that are in the back could make their way to the front, there are many seats in the front here. So if you do that while Fran gets ready, and there you go.
Okay, thank you very much. Thank you so much, Tom. That was very nice of you to say those words. It's a huge honor to be giving this lecture as the Van Allen lecture. And I'd like to point out that two mentors, Margie Kivelson and Michelle Thompson, while a little diminutive in stature, are intellectual giants of our field, and they've been great guidance in the area. So I'd like to thank them first. So this year we celebrate the start of the United States space program, the Explorer 1 first rocket that went up, on which James Van Allen had an instrument that detected the radiation belts. And this was the beginning of the Earth's magnetospheric in situ measurements of the Earth's magnetosphere. This was a cause of celebration at last, excuse to eat lots of yummy cakes, have some fun. But really, this is an opportunity for us to think about planetary magnetospheres for the past 60 years. And if we move to the Earth, I'd like to highlight the Van Allen probes, which have been exploring the Earth's radiation belt for the past 6 or so years. And I show the data from the REPT instrument from the University of Colorado, showing the huge variability in the radiation belts of Earth that vary on timescales of minutes, as you can see, very rapidly responding to changes in the solar wind. When we look at the Earth, away from the Earth towards Jupiter, in fact, the existence of a magnetic field trapping electrons was first observed back in 1955 with the bursts of radio emission coming from Jupiter. And then the radiation belts themselves were detected via synchrotron emission, radio emission that was being observed since 1959. And here is a LOFAR observation taken in Europe fairly recently. I'm showing you a movie at the bottom left showing the wiggling due to the 10-degree tilt of the magnetic field relative to the rotation period of Jupiter, varying every 10 hours. But the top plot shows you that over the past 50 years, the MEV electrons in the radiation belts of Jupiter barely vary by a factor of 2 over all this time. So a very different situation of the radiation belts deeply embedded in the magnetosphere of Jupiter. Now, the Juno mission has been observing in situ at Jupiter, flying over the poles, going through the radiation belts and measuring them. And here you see some observations with the radiation monitoring data indicating that the radiation belts at the horns, at the high latitude regions, as we fly through, are in fact lower than predicted. And so this produces a slightly more benign radiation environment than we feared. And as the spacecraft begins to process down, this may mean that the Juno mission may last a little longer. The other thing that Juno has done with respect to radiation belts is detect a new radiation belt. This is work done by Peter Coleman, who has found that there's a new population near the equator that is produced when energetic neutral atoms. And now these energetic neutral atoms are actually produced out in the magnetosphere with energetic charged particles interacting with the neutral environment around Europa, charge exchanging, producing neutral materials that come barreling into the atmosphere of Jupiter, where they then become charged again. So this is a new radiation belt that has recently been detected. But I'd like to emphasize, highlight my involvement with James Van Allen. It was a huge honor to be invited to work with him on a revision of his chapter in the New Solar System, a book for the public interest. So it's a qualitative book without too much detailed physics. But I helped him write a survey of planetary magnetospheres, which was a great honor, and launched a career where I ended up writing lots of chapters in lots of books and lots of papers, pulling together tables of plasma parameters and making lots of diagrams. And I must thank my husband Crusher, who is a graphic artist who has produced a lot of these diagrams, and I suspect some of you in the audience have used these diagrams. So let's go through looking at some of the planets and talk about magnetic fields. And if you look at the terrestrial planets and you just look at them like this, you would have a hard time predicting which has magnetic fields or not. You probably can already know that it's very bizarre that, for example, our neighboring planets, Venus and Mars do not have dynamos. Why is this? Big question. Now, Van Allen himself said to me when we worked on that chapter, oh, that must be because Venus doesn't rotate very much. Now, I talked to my colleague, David Stevenson, and he says, oh, no, that's not the problem. There's enough rotation just in the orbit. There's a problem with the deep interior. And so there's a big question about our sister planet. Why does it not have a convecting core, whereas the Earth does? There's something very different about that planet. Similarly, with Mars, it's cooled off and the dynamo gone away. And I would argue that we need to have geophysics missions that go and address the interior structure of our two neighboring planets. It's quite a shame that we know so little about Venus. So those are the magnetic fields, but what about the lack of magnetic fields and the interaction of the solar wind with the atmospheres? Now, it's interesting when you look at these non-magnetized objects in the solar system, these are all plotted on the same scale. And you can see, although they have very complicated atmospheres and the environmental plasma interactions with their atmospheres are very different chemistry, different environments, they all end up to being the same scale. And furthermore, the atmospheric loss is almost exactly the same, to within an order of magnitude. Quite bizarre that this is the case, about a few kilograms a second. Okay, so the comets can be an exception when they get close to the sun, but I think it's remarkable, and there's lots of interesting physics to be done here, exploring these different plasma environments with non-magnetized planets. Let's move to the magnetospheres, and there you see there's a huge range in the size of these objects. You could put the whole of the magnetosphere of Mercury into the planet Earth, the whole of the Earth's magnetosphere into the planet Jupiter, and the magnetosphere of Jupiter, while it extends all the way past the orbit of Saturn, would be a tiny piece of the giant heliosphere. And yes, I note that this diagram, as Dave McComas will point out, I'm sure in the next lecture, is now wrong. Okay. So let's start with the small ones. Mercury and Ganymede, about the same size, you see, small relative to the size of the Earth. And these are in very different environments. Mercury is in the solar wind. It has no atmosphere, so it's an interaction of a magnetic solar wind with the magnetic field and the surface and an interior. Whereas with Ganymede, we have an atmosphere, and so the interaction is of the magnetospheric plasma interacting with the atmosphere and the magnetic field of Ganymede, and you can see the aurora here at Ganymede. These two small objects will soon be explored by Bepi Colombo, recently launched. It takes some time to get there, and then JUICE, we hope, will soon be launched. So let's talk about the bigger magnetospheres, and of course here we have the standard idea of what causes the scale, where you have a supersonic flow interacting with an obstacle as per the classic Chapman-Ferraro calculation. And here we balance the ram pressure of the solar wind with the magnetic pressure of the interior and drive this scale for the size of the magnetosphere relative to the size of the planet. But when we look at the diagrams and put this together for multiple planets and scale them according to that dipole standoff distance, you'll see that while there's a factor of 1,000 range in the surface magnetic field, and there's also about 1,000 variation in the density of the solar wind, we end up with fairly similar sized magnetospheres between the size of Mercury to the size of Jupiter. But what's interesting is if you compare the calculated size to the observed size, and particularly Jupiter sticks out as being a planet that is much larger than the Chapman-Ferraro distance. So something else is going on. So why is Jupiter so different from Earth? I've already mentioned that you could put the whole of the magnetosphere of the Earth within the planet Jupiter, but there are other factors too that are important. Yes, the strong magnetic field, which makes it large, but there's also EO, which is an embedded strong plasma source dumping out a ton a second of neutral materials that become ionized. It's rotation dominated with a rotation period of 10 hours, and there's a relatively slow transport rate considering the rotation rate of 10 hours. And this produces a hot plasma disk, as I shall explain. So let's focus on these three things: strong field, internal plasma source, and rotation dominated. So let's look at why Jupiter is so much, has such a strong field relative to the small planets of the Earth and Mercury on the left that have liquid iron cores inside. And then for Uranus and Neptune, the magnetic field is generated in ionic water. So that's water that has enough dissolved ions in it to make it electrically conducting. In the case of Jupiter and Saturn, we have liquid metallic hydrogen, so hydrogen at very high pressures that makes it metallic and therefore conducting. And you can see the volume is enormous in the case of Jupiter. So Jupiter is 11 times the size of the Earth, and yet because of this large volume of the dynamo region, we end up with a magnetic field, a magnetic moment, basically the power of the dynamo at Jupiter being 20,000 times greater than that of the Earth. So this strong magnetic field at Jupiter means that it extends out beyond the orbits of the Galilean moons. And of course, most important is Io, the moon that you can see here covered with volcanoes, those dark little spots. There's about 400 of them, of which about 100 are active, spewing out gases. The white stuff is sulfur dioxide frost. And as New Horizons flew by on its way to Pluto, it saw Tvastar plume erupting, spewing out sulfur dioxide. Now, we have new observations by the Juno GERAM instrument, and this is going to be in a paper that's in process. The infrared pictures just showing you these fabulous glowing regions, infrared images showing you the glowing regions. This is actually around the South Pole of here. So more of that you will see down the road. So the net result of this is that you have Io ejecting about a ton a second of material, becomes ionized, wrapped up in the magnetic field, and there's a strong million-amp electrical current that couples Io to Jupiter. And you can see these emissions in the UV here with the Cassini UVIS instrument glowing, and that's how the torus loses its energy. So what happens is that this is in a rotating system. The magnetic field is rotating with Jupiter's 10-hour period. You fill up a flux tube with plasma, then it'll want to interchange spontaneously due to the centrifugal interchange. And so we'll end up driving material that will move faster outward than inward. Now let's think about the dynamics. We have the ionosphere, the solar wind, and the magnetosphere. If we couple the ionosphere and the solar wind, we get the Dungy circulation of the Earth. If we couple the ionosphere and the magnetosphere, you get the rotating plasmasphere of Jupiter. And if you then couple the magnetosphere, the solar wind, you have an outer boundary viscous interaction. So let's think about the Earth. Here we have a global circulation pattern that is driven by reconnection of the IMF with the planetary magnetic field, driving this global circulation with reconnecting in the tail to close the system. And when we look at the time frame for that global system to work, this is something that Dave McComas pointed out, that on Earth this is a time scale of about 3 minutes. When you go out to Jupiter, the time scale for the flow to move from the nose to the terminator is now hours, and it's extremely unlikely that you can maintain an upstream IMF condition for so long and hence drive a steady reconnection-driven circulation pattern in the system at Jupiter. Alternatively, we couple to the rotation of the planet, and so we have a rotation-driven magnetosphere. And with the flux tube interchange taking mass out, empty flux tubes bringing magnetic flux in, and then at some point you will have some decoupling from the planet. And this is a big question that a lot of people have been working on, and the question is, at what point does the magnetospheric plasma decouple from the rotating planet? How much of that is due to the ionospheric conductance? That was supposed to be a sigma. It somewhere got lost in translation rather than S. The ionospheric conductance versus maybe electrostatic potentials at high latitudes. And what we know is that the communication begins to break down at about 20 RJ, and the magnetosphere and the atmosphere stop talking beyond about 60 RJ. So manifestation of these electrical currents that couple the planet and the magnetosphere is the aurora. And here is a beautiful series of images from Hubble showing you aurora at Jupiter, the north and south poles. You see the main auroral oval. You see a very turbulent or variable polar aurora, which we're trying to understand with Juno. And then you can see the million amp current producing aurora due to Io at various points around the planet. Now, Juno is in orbit around Jupiter, has been since July of 2016, and it's measuring the particles and fields that we think are responsible for these intense auroras and trying to understand what's going on. When we look at the aurora with Juno, on the top right is a UVS series of images that Randy Gladstone gave me of 15-minute averages per shot. And you can see highly variable. We get good resolution when we're close, a little fuzzy when we're further away. And the bottom two images show you images of the same region observed in the infrared and the UV. And what you see is that there are big differences, and these differences in structures tell us about the process of the energy bombarding the atmosphere and what's going on in the atmosphere. At the same time, we're trying to understand what's going on in terms of the processes that accelerate these particles. Is it electrostatic voltages that you might expect if you're thinking about the Earth, or is it waves driven by turbulence in the magnetosphere? And that's what we're trying to explore. Now, Barry Mort gave a talk this morning summarizing all the surprises. I'm only going to focus on 4 of these. One is that, indeed, instead of seeing the indication of a steady electrostatic acceleration by potentials, it looks like we are seeing a broadband acceleration in a stochastic fashion with, in fact, there's many electrons or more electrons going up as going down to produce the aurora. We also see variations in the electrical currents that are much weaker and seem to be stronger in the south than north. So these are all puzzles we're trying to understand. Now, a recent paper by Joachim Sauer was particularly useful because he's been looking at these data and thinking about it, and he, doing a theoretical study, says, well, let's think about the role of alphane waves that move along from the plasma sheet to the auroral region and back, and how they interact with the surrounding plasma. Now, close to the planet at high latitudes, they seem to be accelerating electrons along the field, and this is producing the electron beams that we see going in both directions. And then further out, the dissipation of these alphane waves seems to be heating the ions in the perpendicular direction. And so both in close and further out, we're heating the plasma as it moves away from Jupiter. So what we're seeing here is indeed that maybe this system is quasi-stable, that we have strong coupling currents. In fact, those currents may be so strong that they become unstable and break up into smaller, maybe time variable current structures. We clearly do have flux tube interchange, but Joachim Sauer points out this is in fact inherently non-continuous and therefore somewhat out of force balance. And this seems to be driving turbulence, which maybe cascades down to small scales, driving stochastic acceleration of the electrons. So this is a fairly new view of what's going on at Jupiter, and we're trying to put together some idea of what's happening. Now, as you move away from that auroral region, out into this vast magnetosphere, you see that plasma heats up as it goes out, tapping the rotational energy via these field-aligned electrical currents. But also as the plasma comes in, because you've got this interchange of flux tubes, you have adiabatic heating, and there are places where after a plasmoid being ejected down the tail, you have a dipolarization bringing in energy again to the inner region. So you have heating both inwards and outwards, and you have a very hot plasma. In fact, if you calculate the local plasma beta, that is the ratio of the thermal energy to the magnetic field energy density, you find that it's greater than 100 throughout a lot of the plasma sheet. And I believe this is the only place in the solar system where we have a consistent large volume of plasma where the plasma beta is greater than 100. Now, the consequence of this high beta plasma is to change the move away from flux tube interchange into maybe ballooning instability, or maybe we move to small scales where we have small scale intermittent reconnection in the plasma sheet, small plasma blobs going down the tail, or maybe even kinetic scale transport. So this is all new ideas, a very new environment, very different from the Earth, where there's a lot of interesting plasma physics going on. Another consequence of the high beta plasma is we can now explain why the Chapman-Ferraro doesn't work with just balancing the ram pressure with the magnetic field pressure. You have to add in the thermal pressure of the plasma inside. This makes the magnetosphere very compressible. So comparing with the Earth and Jupiter, and you think about what happens when you increase the ram pressure by a factor of 10. The case of the Earth, you have a very stiff dipole, only decreases by 70% to 70%. With Jupiter, it reduces by a factor of 2. And this explains why we seem to see this big range in scales of the magnetosphere of Jupiter. Moving to the outermost region, I think we have a solar interaction with the magnetosphere. It's a viscous interaction where we have small-scale intermittent reconnection on the boundaries, driven perhaps by Kelvin-Helmholtz instability. And so we have a thick boundary layer around the edges with blobs going ejected down the tail at the center. So really, in some ways, I would like to think of this as a big disk magnetosphere with a tail, so somewhat like a real colossal comet with Eo's material being ejected down the tail. Future missions, Europa and JUICE, they will both be carrying particles and fields instruments, which will be very important for measuring the environment around the satellites. We hope those will soon take off and be on their way. So why is Saturn and Jupiter so different? They are very different in scale. Although they're similar as planets in size, their magnetospheres are very different. Factor of 3 difference, more or less, you can see here on this scaled picture. And the reason is simple. The first reason is a weak magnetic field. So although Jupiter and Saturn are similar in size, Saturn's about a third the mass of Jupiter, and so the pressures where you have metallic hydrogen are much deeper down, and so it's a much smaller dynamo region with a much weaker field. The other factor is the plasma source. Now at Io, we have this half ton a second of plasma, a ton of neutrals, half of which becomes plasma, and whereas at Saturn, small little Enceladus produces a mere 50 kilograms a second. In addition, the pickup energy of say an O+ ion at Io is 270 eV and a mere 58 eV at Enceladus. So this makes a big difference when we look at the mass and energy flow through this system. At Jupiter, here we have the Io plasma torus with half of the material going out through charge exchange, out as fast neutrals, half being transported out in the plasma disk, whereas at Saturn, we have nearly all of it being removed as fast neutrals, with only a few % going into the plasma sheet. The other reason is the energy. When we look at Jupiter, we have about half of the energy coming from pickup ions and half from hot electrons, most of the energy coming off as UV emissions, whereas at Saturn, again, charge exchange is the dominant loss process. So the net result of this is when we look at Jupiter and Saturn, you can see there's a huge difference in the roles of the plasma to the neutrals, and you can see here in terms of the total amount of neutrals, the amount of plasma, and you do that, those ratios, you'll see it's about 4 orders of magnitude in the ratio of neutrals to plasma. And the net result then is to have a much smaller plasma disk, lower energies, and much less auroral power because of the neutral dominated nature of the magnetosphere and the weaker magnetic field at Saturn. Lastly, I would like to mention Uranus and Neptune. And this is partly because I've been advocating for these missions for a long time, but I would also like to think of James Van Allen, who worked very hard in the 80s to push for the Galileo and the Cassini missions when in his role working through the Academy and with NASA committees and so on. And so in honor of James Van Allen, I really want to push for a Uranus and Neptune mission. We need to go back to those planets. So when we look at the magnetic fields, which we just got a tiny glimpse of when we flew by with Voyager, is that we see that unlike the Earth, Jupiter, and Saturn, which are pretty much dipolar with some modest non-dipolar components, when you look at Uranus and Neptune, you see highly non-dipolar magnetic fields. You can approximate them as highly tilted offset dipoles, but they're really very irregular magnetic fields. And so when you look at the magnetospheres that we flew through, we saw very irregular changing magnetospheres. And we don't understand really how they respond to the solar wind because it's changing, the configuration is changing on the time scale of a rotation. Now, there have been some hints of aurora at Uranus with HST, but what's really interesting is to look at these models of the magnetosphere of Uranus, and because of the Uranus being tipped on its side, you can see there's going to be huge changes over the season for Uranus. And so I put a red line there indicating if we were to launch relatively soon a spacecraft, this is the epoch where we would be able to observe this weird magnetosphere of Uranus between solstice and equinox, and we could get some good coverage from orbit. We should be carrying modern instrumentation and thinking about how to minimize the amount of communication we need with decent onboard data processing that we can do these days. So there's been a study of these ice giants missions, and if we use conventional launch vehicles, we will have about a 12-year flight, even if we're using Earth-Venus gravity assists. But, you know, and we do have the plutonium we will have enough to do that. But what we really need to think about is maybe we need a little bit more of a beefy launch vehicle, SLS or Falcon. I don't have an opinion one way or the other. We could get there in a reasonable amount of time, more like 5 to 7 years, and carry more mass out there. So in the spirit of Van Allen, let's go do these missions. There's huge, exciting science to do, not just space physics, but of course, you know, the planets and those moons. But the magnetospheres are truly magnificent, and we should go back there. So let me finish my comparative planetary magnetospheres, summarizing here all of these planets, the huge range in the magnetic moment of these different planets, a corresponding range in the sizes of these magnetospheres, and also the coupling processes which differ between the rotation-dominated Saturn and Jupiter compared with the other ones, which are much more driven by coupling between the surrounding plasma and the magnetic field. But look at the difference in timescales between these different magnetospheres, big ranges in timescales, and lastly, let me emphasize all those question marks at the end for Uranus and Neptune. We have spacecraft going to the other planets. Let's go back to Uranus and Neptune. And with that, I will thank all the people who have been helping me over the years to try and understand planetary magnetospheres and space physics and exploration of our solar system. I thank you all very much.
All right, we have time for some questions, please. And there is a microphone, so if you'd like to approach the microphone and come up, and it is unfortunately a little hard for us to see people who would like to ask questions.
Nobody has any questions. Who did I miss off?
All right. Well, if there are no questions, oh, sorry, we just. There we go.
Yeah.
Sorry, Nick.
So,
I think
yeah.
that's Nick, right?
Yeah. So, Fran, I have a speculative question for you that you can either punt on and take a more serious question or not. Suppose we were having AGU on Europa. How would our understanding of magnetospheres change?
Oh, well, we'd be dead within hours because of the radiation damage. So, I mean, yeah, kind of a waste of time.
If you would
Right.
mind us.
Sure. Of course, I would advocate sending, and this is again in the spirit of Van Allen, I would advocate sending robots, not humans. There's nothing that humans can do in space the robots can't do more efficiently, cheaper, better, and so on, except tourism. And I don't think an AGU is tourism. So I would advocate we send robots. And how would we see things differently? Well, what we would see would be more like those early diagrams I showed of the plasma interacting with an atmosphere. And indeed, trying to understand how the plasma interacts with the atmosphere and the surface, maybe delivering important ingredients to the surface for the life that may exist down in the oceans, then I think we would have a slightly different emphasis. And that's exactly what Clipper is going to go and do and explore.
Thank you. Is that Drew there behind the lights?
So,
Yeah.
Realistically, what kind of instrumentation would you like to see on board Uranus and Neptune missions? And in particular, I'm interested in how they'd be different.
Well, of course, we've come a huge way since the days when the Voyager instruments were built. Of course, the LECB instrument still has a stepping motor and it interferes with the plasma instrument. No, I didn't mean to say that. We would make an LECB instrument that doesn't have a stepping motor and interferes with the plasma instrument. I think, I like Faraday cups, so I would send a bunch of Faraday cups, or I actually have a new idea for a new Faraday cup we could talk about. That would be able to look at different angles, different directions. But you'd send a plasma instrument, you'd do an energetic particle instrument, preferably with some overlap. You'd have a magnetic field magnetometer. And then you would probably want a UV instrument and a thermal instrument and a camera. Of course, you have to have a camera. Usual suite. But the beauty of the modern era is we've taken those instruments and we've reduced them in size, reduce them in mass enormously. Now, we still have to communicate with Earth. We still need to communicate with Earth and send the data back, right? That's not a miracle. You still have to do that. But I think doing modern onboard data processing would be extremely helpful because, it's hard to communicate out there to the outer solar system. And so you might want to do a lot of onboard data processing. So my instrument, the plasma instrument, I would argue for doing onboard calculation of density, temperature, and flow speeds. And then you would send those data back and you could intelligently tell in your communications, you might want to go and look at this particular time because it was really weird and go back and get more of those data. But where it's well behaved, just send back a limited number of information. So I think there's lots of ideas that we could save resources and make this mission happen a lot in a, say, New Frontiers Plus size mission. Let's do it. What do you say, Jim?
You gotta stand up and shout.
Stand up and shout, please.
I've heard you talk before about the icy moons of Jupiter or Europa in particular being a good place to look for life, better than the terrestrial exoplanets. But okay, what are your thoughts on the habitability of the liquid waters on Neptune, for example, versus Europa?
So it will be interesting to think about how habitable the oceans are, the ionic oceans on Uranus and Neptune. And to be honest, I haven't thought about that. My concern is that they're still 80% of the radius, I think, at a generous distance. So it's a long way down through that hydrogen outer layer of the atmosphere. And you and I had a conversation yesterday, so you know this. We don't know whether or not, does anyone in this room know, could you swim in that ocean, or would the pressure of hydrogen be so great that you would be crushed? And what is the surface tension like on the top of that ocean? Could you walk on it? Could you swim in it? What is it like? I think we have a lot of things to look at, and I encourage people to go out there and think about Uranus and Neptune and all the cool things that we should go explore.
Sorry, question back?
Yeah. Oh, can you see me, Larry? Okay. A quick question. Oh, very nice presentation. I really enjoyed it. Thank you. So in your point of view, or what the planetary science will be in next 10 years, or even further?
So I think for planetary exploration, I think we are moving in this direction of smaller satellites, but I would also like to see us go into multiple satellites. The first thing I think we need to do is to send a whole bunch of small sats to the atmosphere of Venus and go and explore that solar wind interaction with the atmosphere of Venus. We could test out aerobraking, for instance, that would be very interesting. Let's try out different small sat technologies at Venus and try and understand that Venus interaction with the atmosphere. Eventually, let's start working on getting through that atmosphere to the surface to do seismic studies. Now we have the InSight just landed on Mars and is going to be doing seismic studies of the interior of Mars, maybe trying to help us understand what happened to that core inside and why the dynamo turned off. I would love to do the same at Venus. I know it's challenging, but let's go somewhere difficult for once, not just keep going back to Mars. So I think it would be good to go to Venus and try and understand, what it's like inside. Why is our sister planet so different from us? I mean, I just find it extraordinary that we haven't put the energy and the effort into Venus. I don't have anything in this because it doesn't have a magnetic field, so I'm not going to be involved in that. So I'm pushing it as a planetary mission that we should be doing. So Venus is a major target, lots of small satellites. Let's go thinking about doing things with multiple small satellites. One of the big problems we have in space physics is we don't understand spatial and temporal variations. So that's why we have 4 MMS spacecraft in orbit around the Earth, to try and sort out spatial and temporal variations. So please, can we just do 2 to go to Jupiter, please? I think I've said enough.
Another question?
Oh, there. There's a hand.
Sorry.
I'll beg you with the question, Fran. Do we have anything to learn about planets and magnetospheres by looking at exoplanets?
So the difficulty with exoplanets is detecting that they're magnetospheres. And I know that radio astronomers have been looking at exoplanets for years and years and years, and every time I see Philippe Zarka, I don't think he's here, but usually I see him once or twice a year. He says, I think we have a candidate. Any second now, we're going to declare an exoplanet has a magnetic field from the radio mission. And it's not happening. So I think it's very hard. It's very difficult to do that. We can make wild speculations, and there's a gazillion exoplanet papers in ABJ all about, let's take my model and do a study of what's going on with an exoplanet around whatever. But it's really difficult to do it. We need in situ measurements to really explore magnetospheres. So it's very difficult to do exoplanets. I think that we have lessons that we can teach the exoplanet community if we just go back to this range of things that we have in our solar system, not to mention the ones like Venus that don't have a magnetic field. Of course, we have a lot of things. There's a lot of plasma physics, a lot of planetary science to be learned from this. But I think we got a long way before we really start exploring exoplanets of outer magnetospheres of exoplanets.
So that's
Andy?
Oh no, he's going to ask me about the source of the ionosphere at Jupiter.
So facetious comment kind of reacting to the exoplanet. It's a historical comment. In the mid-1970s, Mike McElroy said, I'm not going to work on planetary science anymore because there's data to contradict it.
Ah.
What you said about exoplanets, we can do a lot of theories, but you need data to really...
Yes. So we need data to explore the exoplanets, and that's tough when you're just doing remote sensing. Space physicists like in situ measurements, and that's going to be tough with exoplanets. So you can speculate as much as you want, but it'd be nice to have some real evidence.
If we have time for one more question. Sorry, it's very hard to see over here. Sorry about
Oh,
that.
yeah, there's one here.
With regards to exploring Uranus or Neptune, do you think it would be better to do a kind of flyby of both planets or to orbit around one of them?
Okay, the question then was, do we want to do a flyby of both Uranus and Neptune, or do we want to do an orbiter, two separate orbiters? I would argue for two separate orbiters. It just is, there's too much to be done at each of these planets that just a simple flyby is not going to give you what we really need. Now, there are some people who may argue otherwise, but I think we just need to do a mission to each. And to explore them. Each is very different, all have very interesting differences and similarities. I think it would be fantastic to do. And there could be some economy of designing two spacecraft, one going to Uranus, one going to Neptune. I'm not sure about that, but you know, you guys get out there, do the studies, and push and push and push. Let's make this happen.
All right, with that, let's thank
Okay.
Fran again.
Thank you.
So we'll take a very brief interlude to exchange, and we do the picture-taking ritual, and then we'll go on to David McComas's talk.